All right, I'll get started with the introductory part of this webinar. We're so happy to have you join us today, and we are very excited about our panel that we have present for today's discussion. So the topic of today's GCE Ask the Experts webinar is Slope Design, the Geotechnical Model. And this is, like I said, an Ask the Experts webinar, which means that we have an expert panel here present, and they are ready and willing to answer your questions, which we will invite you to submit live throughout this webinar on the topic of slope design, the geotechnical model. This webinar is going to run for 1 hour or until we run out of questions, which I don't think has ever happened to this point. And this webinar is brought to you by the Geotechnical Center of Excellence here at the University of Arizona, where I'm joining you from today. We are an industry-funded and member-led interdisciplinary center, and we focus on collaborative geotechnical research and education with the goal of bridging gaps within and between academia, industry, and fields of study. If you'd like to know more about the GCE or any of the professional development courses that we offer, our research projects, send us an email to either gcecourses@arizona.edu with regards to our professional development program, or just gce@arizona.edu for any general inquiries. And the topic of this webinar today, the geotechnical model, does correspond to a section of a course that's currently running within our professional development program. And that course is the Fundamentals of Open Pit Slope Design, which focuses on all of the topics that you see here, which the geotechnical model is one of those topics. If you're interested in this course, we will, I think, put a link into the chat for you guys, or you can quickly scan this QR code before I move on to the next slide. And of course, we need to acknowledge our wonderful members. As I mentioned, we are a member-led organization. So we have on this slide all of our GCE membership group members, including our executive members, leadership members, and partnership members. And without our members, we would not be able to do the research we do, to put together the courses that we do. So we want to make sure to give them a big thanks for all of their support for our center. And the course referenced is underwritten by the Large Open Pit Project, or LOP. So we'd also like to acknowledge them for their support. And it is based upon a book which was put out by the LOP, the Guidelines for Open Pit Slope Design. If you're interested in that book or to find out more about the LOP, you can go to lopproject.com. And now to introduce our team here today. Myself, I'm Jillian Noonan, Senior R&D Engineer with the GCE, and I'll be your moderator today. Along with me, I have some members of the GCE team who will be assisting with the webinar, including Cheryl Bukowski, who is our Professional Development Program Lead. Hello, Cheryl. Thanks for joining and helping out.
Hi, everyone. Thanks for being here.
Also, Christian Ortman, who is a computing sciences researcher with the GCE. Hello, Christian.
Hello, everyone. Thank you for joining us today.
And Allison Brucey, who is our program coordinator. Thank you, Allison.
Thank you, Jillian. Thank you, everyone, for being here today.
And now on to our expert panel. So we're very fortunate to have a great panel here today of top-notch experts who are going to be answering and addressing all of the questions today. Starting with Ed Saunders. Ed is a principal consultant and practice leader with SRK, and Ed also provided a course module for the Fundamentals of Open Pit Slope Design course on geotechnical domains. So thank you so much, Ed, for joining our panel today, and thank you also for your contribution to the course.
Thanks, Jillian.
Next, we have Andrew LaRich, who is a senior rock mechanics consultant with SRK. And Andrew was also a course presenter in the Fundamentals of Open Pit Slope Design course, providing a module on defining design sectors and sections. Great to see you, Andrew, and thanks for joining the panel.
Yeah, thanks for having me, Jillian.
Also on our panel today is Sarah Cox. Sarah is a senior rock mechanics consultant with WSP, and Sarah contributed to the course with a module on building the geotechnical model. Thanks for being here, Sarah.
Thanks for having me.
Also joining our panel is Scott Silwick, who is Vice President of Colin Nicholas and also one of the lead technical advisors for the Fundamentals of Open Pit Slope Design course. Thanks, Scott.
Of course, happy to be here. Hi, everybody.
And we have Karen Moffett, who is President of Equilibrium Mining and also one of our lead technical advisors for the course. Thanks so much for being here, Karen, and for all your contributions to everything.
Thanks, Jillian. Hi, everyone.
And Julia Potter, who you may know as the Director of the Geotechnical Center of Excellence here at the University of Arizona, will be a panel member today. Thanks, Julia.
Thanks, Jill, and to everybody for joining us. I'm looking forward to a great discussion.
And Lauren Lorig is Principal Consultant with Itasca, will be joining us on the panel today. Thanks so much, Lauren, for lending your time and expertise.
Yep, happy to be here. Looking forward to it.
And finally, we have John Beck, and John is Senior Geotechnical Engineer with Rio Tinto, currently at the Bingham Canyon Mine. John, thanks so much for joining us. We really appreciate you being here on our panel today.
Yeah, thanks for having me.
All right, so for you, those of you that are joining us as participants, I'm just going to quickly run through how you can interact with our panel today and participate in this interactive webinar. So first of all, since it is a webinar, your video is off and you are muted, but there are ways that you can submit your questions for the panel. And the way we suggest is the Q&A function, which is a button on your control panel. If you click on Q&A, it should pop up a window where you'll be able to type in a question. You'll also be able to see questions that other people have submitted, and you can vote for those with a thumbs up. So if you see a question you like, you voted a thumbs up. Questions that are highly rated, we will move those to the top of the queue. You are able to enter your questions anonymously by selecting a checkbox. And let's see. And also just to let you know that this is a recorded webinar, so we'll be posting it when it's finished to the course site on D2L and also to the GCE's YouTube page. And just a note that this webinar and all the discussions herein are intended for educational purposes only. All right, thank you so much, everyone. I think we're ready to get started with questions. So how this will go is we have some pre-submitted questions that have been received through the GCE, either email or survey or course site. And then we'll also be starting at this point accepting all of your live questions. So I welcome any live participants to go ahead and start entering questions into the Q&A at this point, and we'll grab from those as well. But first, a question that came in, I'll first direct this towards Ed, because it's regarding the content within your teaching in the course, which was the geotechnical domaining. So the question is, I understand that when creating geotechnical domains, that knowledge is often limited until the actual pit is exposed during mining. So what is the typical degree of confidence that domains are defined in for early stage design? And I guess any way you want to quantify that would be fine. And how is that uncertainty communicated? So Ed, I will throw that one to you first, and then we can open up to the panel for additional discussion.
Okay, thanks, Jillian.
Thank you.
Start with a hard question. Thank you, Richard. Yeah, I think there's probably many ways that we could address this, but I think for me it goes back to the geological complexity. So if you're in an ore body that's relatively simple, then your confidence may be quite high through the study stage. Whereas if you're in a fairly difficult deposit with lots of alteration, etc., I think no matter how much data you have, you're always going to have a lower level of confidence, even with lots of data, right? So it's probably an open-ended question, and I probably won't address it very well, but I guess there's always going to be uncertainty through the study phase. And if you can just relate that back to the deposit setting, you're going a long way to addressing that. I think for me, in terms of communicating, it's not getting too hung up by statistics or any of those things. It's really kind of a traffic light system. and your judgment based on experience in similar deposits. That's kind of where I would say with communicating the uncertainty. Lots of figures and just so essentially you're communicating through figures, sections of where you're confident, where you're not confident, and particularly understanding those geological controls. And where you're uncertain in those controls, just make sure that's pretty clearly stated in figures. So I haven't really addressed that too well, but I see Lauren's got his hand up there to help out.
Yeah, I think you spurred off the discussion though very well. So we'll pass over to Lauren.
Yeah, so I was reminded while you were talking, Ed, about and based on experience, there's a pretty good paper in the Slope Stability Conference that was held in Tucson in 2022, and I forget who all the authors were, but Pedro Verona would have been one of them. And they reported on a benchmarking study that was done by Antofagasta Minerals and Codelco, covering, I think, all of the porphyry copper deposits that they operate in Chile. So it's a pretty good number of open pits. And what they did was they went and looked at different stages of projects from conceptual all the way to final design, and they reported on all kinds of data. So meters of geotechnical holes, numbers of laboratory tests of different types, things related to hydrogeology and so on. Their study, started out to come up with guidelines, and they struggled with that. And the only thing that they felt they could do would just be to report on this benchmarking exercise, which is quite good. So I think that's a starting point, at least for porphyry copper deposits, and it's one of the better ones that I'm aware of.
Thanks, Lauren. And I'll just note that Julia put that paper into the chat. So you can grab that there. Scott, do you have something you'd like to add?
Yeah, just with regard to how the confidence is communicated, that in geotechnics, we've kind of adopted the same terminology that's used in exploration geology as far as scoping level, pre-feasibility, feasibility, and operations. And so I found that's a good way to communicate to non-geotechs kind of what the confidence is in our geotechnical design parameters. And it's okay for a certain deposit to have different sectors of the pit or different parts of the mine that are at different levels. So at the end of a study, we might say that this sector is at what we feel to be feasibility level from a geotech perspective, where this sector is still at pre-feasibility level. And then I found another good way to communicate that uncertainty is that if you aren't sure what a certain parameter is based on the data that you have, you can just do a sensitivity analysis. So if there's a certain rock type where we don't have any triaxial testing, we don't know what the MI value is, just do a sensitivity. Say what's the upper range of what the MI value could be, what's the lower range, run both those analyses, and that way you can present to the stakeholders or to management, this is what the worst it could be based on our data is, this is what the best it could be, and then you can make the decision whether or not it's worth investing the money to go collect the data for that parameter.
Good, thank you, Scott. And I would welcome anyone else on the panel to go ahead and unmute if you'd like.
I can add one thing, I think, to build on what you said, Scott. I think particularly early on, communicating that uncertainty can also be used as a bit of a carrot when you're working either with your mining team doing the design or with the client itself in terms of trying to focus their eyes on what does that next round of study look like and where should their energy and efforts be spent to improve the reliability of the design that we're giving them.
Thanks, Andrew.
And I would say, like, it becomes particularly particularly critical on the implementation side to like communicate that all the way through to the operators. But then also involve them, and this is getting maybe into a little bit more of the execution side as opposed to early stage design. So we're maybe off topic, but including operators and people within the broader technical group into those discussions to like as was previously mentioned, like having good visuals of like what we know and where we know it, but then also what we don't know and where we might have a lack of data supporting some of those key decision points. And so, yeah, I think, in working close within like a broader technical team also helps like kind of pull in focus and like craft that message of uncertainty and how when the rubber hits the road, if you will, like how that might play out. Yeah.
Thanks. Good points, John. It is quite a broad question, a great question, and an important topic. Anything else that the panel would like to add before we move on to another? All right, well, thank you, Richard, for the question. And thank you to those of you who are in our live group who are already submitting questions into the Q&A. We will be pulling those up in just a moment. But first, I'm going to grab one more pre-submitted question. And this one is for, let's see. Since we're on the topic of geotechnical domains, let's just stay there for a moment. So I'm going to, again, if Ed is willing, ask Ed to either first address this or pass along to another panel member. But this question came in with regards, again, to geotechnical domains topic. So when you are determining your geotechnical domains, specifically defining the specific boundaries, how much of that is done manually by the practitioner, so subjectively decided, versus automated? And are statistical methods typically utilized? So Ed, if you're willing, I will first send that one to you.
Yep, no, thanks, Jillian. Yeah, it's a good question, and I think probably it varies between approaches from others, but I guess for us, and I'll speak for Andrew as well, is a lot of it's done manually, pulling in geological data, geotech data, into things like Leapfrog, and spinning around your models and looking at changes and patterns. Very important for structures. Like a stereo net tells you a 2D image, but what does it look like at 500 meters depth? Very different than the poles in a stereo net. So I'd say that you really have to spend a lot of time manually looking at it. Then you start to pull in your stats. If your stats support your kind of impression or your knowledge on the geological controls, then you're on the right path. If your stats are, I'm talking about like histograms of data, if your stats are telling you you've got bimodal distributions, and then go back to your 3D model and look for why you see differences in those distributions. So it's kind of hand in hand, but certainly for our team here, a lot of it's manual and looking at structures and then rock mass and a lot of Leapfrog type work, right?
Good, thanks, Ed. Any other panelists like to talk to this question? Feel free to unmute. Go ahead, Julia.
I agree with Ed. I think that, and I'll apologize to the group, my voice is a bit scratchy today due to some over talking at a conference last week, but I'll do my best. I agree with Ed. A lot of it is kind of visual or manually done. I think that often us as the geologist or engineer has the best understanding of where those boundaries need to be drawn and our observations need to be considered in judgment. I did present at SME last week on geotechnical block models. And one thing that came up was an example using indicator models, which are basically just models of the probability that a value falls in one category or another. The example that was used is if your JA value is greater or less than 4. How you can sometimes use those if you're having a hard time seeing your way through what might be a complex data set to help draw some of those boundaries. So there are statistical methods that can be used, but I would say those are probably secondary to everything that Ed just mentioned.
All right, any other comments?
Yeah, I definitely agree totally with everything Ed and Julia just said. It's all really great. Just to the early career professionals out there, I thought I'd throw in that when starting the domaining process, you always want to start with the geology first. So, before you start this process for any property, make sure you read up about the geology, understand the sequences of how the rocks were put down, what the different alteration types at the mine are, and go into the domaining process, thinking geology first, and then overlay your geotechnical data on top of that and see how things might shake out, right? Every rock type boundary may not need to be a geotechnical boundary, depending on what the geotech data looks like. But just that, the process to me should always start with the geology.
I think that's a great point, Scott. And that actually also came up in discussions last week. And I think what was essentially the point was that if you don't have an underlying geologic reason for a boundary being there, that you probably want to dig a little deeper because there might be something that you're missing.
And then beyond that too, I agree, start with the geology, but look to whether or not you need the subdomain beyond that. All too often I see people use lithology as the key driver for the geotech domains. And then within within each of those domains, you've just got such a high degree of variability because you haven't looked for those subdomains, if you will.
I just want to add one more thing. I think it might have been touched on, but just to reiterate what everybody's saying is the amount that you know your data and you know your geotechnical setting and environment helps a lot. And if something isn't making sense, go back to what you do know. I think was key in a lot of our modules as well, just how well you know it.
All right, thank you all. I'm going to next pull up a question from our live group, keeping us in the general topic. And since I've called on Ed so many times already, maybe Andrew, if you wouldn't mind starting with this one, if you're willing. I think this might also relate a bit to your presentation where you were talking about design domains and or sectors. So the question from Jaime, what would be a reasonable approach to establish geotechnical domains in anisotropic rocks, for example, schists? And how relevant would it be to acquire fold axis, crenulation, and other structural features? And also considering that you were presented in the structural geology course, I feel you might have some input to this question. Andrew?
Yeah, thanks, Jillian. Yeah, I think super relevant to the presentation that I had given. I think this kind of speaks right to getting back to once you've established your domains, what are those domains going to perform like in the pit that you're designing? And so in the case of anisotropic rocks, the performance and the instability considerations in the footwall. So when that anisotropic fabric is dipping out of your slope versus dipping into your slope is markedly different. And so you have to have your mind to that as a starting point. Drawing on some experience, more on the structural geology work in iron formations, understanding your deposit geometry is critical, and that changes down the length of your footwall, for example. So being able to identify where those fold axes are, characterizing those, when you expect the orientation of that folded deposit to change, to shallow out, and potentially give you more grief at the bench scale or worse is really important. So you have to have your mind on that for sure when you're in these sorts of deposits, is understanding that in many cases, particularly when you're on the footwall side of things, being able to properly characterize, particularly in 3D, how that fabric might be changing is the first and foremost, the biggest thing in those deposits when you're doing your design work.
I knew I called on the right person. Andrew answered that really well, but are there any additional thoughts from the rest of our panel? I'll open it up.
Oh, I'll jump in, Gillian. Probably speaks to a point just earlier is don't make too much interpretation too early with your stereographic projections. This speaks to like the complexity. It's understand your major fault, your major joint or discontinuity patterns. Understand if that fold axis is your domain boundary, and then start looking at patterns in 3D. If you find that you're doing too much interpretation too early, you lose sight of the actual change in patterns and those types of things as you move through the anisotropy changes, etc. Right? So it's bringing everything into 3D and seeing changes of patterns as you move through the deposit.
One anecdote I could add to that, that Ed and I have worked through recently is in a deposit like this, the footwall design being based on the average foliation angle, and what that opens you up to is risk that up to 50% of the actual bedding that's been measured across that footwall has the likelihood of undercutting your benches and that not being adequately factored in. And I think that's where Ed's comment around not doing it solely based on a single stereo net and doing it ideally in a 3D space with some kind of idea or thought to geologically what's going on in the background is the approach you need to take in these sorts of deposits.
Thanks, Andrew. Lauren, do you have something you'd like to add?
Yeah, I was just going to say, in my experience, these are sometimes some of the most challenging environments to work on, depending on how tightly things are folded. Sometimes it's really tough to know what the orientation is going to be, because you can't get enough boreholes in there to define these things, and it's tough. It's really hard, particularly the bench behavior, and depending on what the scale and sort of wavelength of the folds are, it can just be a nightmare.
Just to add one more thing onto what Lauren said, that if you're working with borehole data in a deposit like this, in a rock type that's extremely anisotropic, you really need to be careful about watching the blind zones in your televiewer drill holes. So basically, if you drill a televiewer hole, you're not going to be able to see structures that are parallel to the borehole. That'll be the big blind zone. And then there'll also be a smaller blind zone that's perfectly perpendicular to the televiewer hole. And I've seen it a couple times where there's different holes around the pit, and people look at the data and say, "Oh, look at the stereo nets. This wall, the bedding goes away. There's no bedding on this wall." But it's like, oh no, it's just because we only have one drill hole and our bedding's in the blind zone in that drill hole. Definitely something to keep in mind when working in a rock mass like this.
All right, good tip, Scott. Lots to consider. Jaime, hopefully we answered that question well for you. Are there any additional comments from the panel before we move along to the next question? All right, thank you so much for that. I'm going to pull up another question from our live group, and I will just let everyone in the webinar know we have about 30 minutes remaining in this session. And if you have a question related to open pit slope design, the geotechnical model, and you can put that into the Q&A, and we will do our best to address as many questions as possible during our session today. Okay, so here's another question that came in from our live group. I'm not sure if we have any geochemists on our panel today, but perhaps there may be some comments you can provide. for the person who posted this question. Is there any knowledge in our panel with regards to incorporating geochemistry into open pit slope stability, and anything on the confidence of modeling geochemistry? Have you encountered that in your studies? And I will just open this up to the whole panel. If anyone wants to unmute and comment on this question, please go ahead.
I guess I'll jump in with some experience from a mine I was working at previously, where we noticed this mine had a wide variety of fault infill types, and we ran XRFs to better understand the geochemistry or the chemical makeup of these fault types. And it showed that there was a pretty strong correlation between like the frictional properties of the infill type based on the percentage of or the prevalence of talc. And so we were able to sort of quantify like that relationship, and then we were able to sort of apply in our stability models varying strengths based on the presence of talc. And so that was a way in which we were able to like make more geological or geochemical observations and sort of quantify that, and then relay that back into like stability results, specific stability results, at least on the modeling side. Obviously, there's a bit of back analysis calibration that was required, but it's definitely like something that has high value, but oftentimes is potentially elusive. You could end up wasting a lot of time and effort on chasing things down, especially. But in this circumstance, like there was a high variance in strength of that material type. And so, you know, we saw value in pursuing that sort of line of questioning.
Interesting, John. Thanks. Andrew, you see you have your hand raised.
Yeah, I think that last point, John's a good one. You know, I think the answer to it really comes into what deposit you're in, and can you easily or efficiently kind of connect the dots between what you're seeing in the geochem versus your rock mass condition. You know, I think back to a project we worked on last year in a structurally hosted gold deposit, early stage, you know, really limited geotechnical data. But the one thing we were able to tease out is with gold grade and structure came a spike in arsenic. So what was important to the resource geologists in terms of deleterious elements, we were able to really quickly relate that back to rock mass condition. And in particularly in early studies where you have limited geotechnical data, but the resource definition tends to be well in front of our geotechnical work. That was quite useful to us to kind of get the domaining process going to identify those weak zones using geochem. So there's certainly cases where it can work, but I think like John said, not always the case. And sometimes you can go down that path without coming to a solution or some sort of relationship that you're looking for.
All right, thanks, Andrew. Any other comments from the panel before we move along? All right, I'm going to swing it back around to the topic of block modeling. And Sarah, I'm going to send this question your way, which was pre-submitted. Kind of a yes or no answer question, but hopefully you'll elaborate a bit. So the question came from Marina, and it is, do you always need a block model for slope design?
I mean, the immediate answer is no, definitely not. You know, a block model gives us a 3D representation to estimate between the data that we do have. So it in theory, we want it to help us make more educated guesses on you know, areas of limited data. but there's plenty of ways to, I guess, model the data you do have with the domains you have and stuff. So that's the short answer is no. And I guess the other side of that would be, a block model might not be best considering the data you do have. So if the data is unreliable or whatnot, your block model is not going to be reliable either. So I guess I'm going to throw that out to the panel. I'm sure everybody has a
Yeah, absolutely. I see Lauren has his hand raised. Go ahead, Lauren.
Yeah, well, the obvious question is, what's the modes of deformation and failure? Not all of them involve rock mass quality and strength. If the design and the slope performance is based on structures, block model may not be necessary at all. So it's important to have a conceptual idea of what the slope behavior is going to be to decide whether a block model is useful or not.
I agree with what both Sarah and Lauren said, and just want to touch back on what I think Sarah was getting at in the last note, which is that in some cases, if you don't have a fair amount of reliable data, I think block models can give a false sense of precision. If you're building one off of minimal and unreliable data. And so I think that they can be a bit dangerous sometimes. I've developed a lot of block models, and when you send them off to somebody, if they're not accompanied with the right kind of documentation to indicate the level of uncertainty, et cetera, they can be kind of taken at face value. And I think we've all heard the adage that all models are wrong. It's just a matter of how wrong they are. And so the less data you have and the less certain you are about that data, the less reliable your block model is. So I think it's important to think hard about whether you have sufficient data. And as Lauren said, the use case, do you really need that to evaluate the given slope that you're interested in?
Good, thank you. Any other comments here? All right, I'm going to pull up another question from our live group from Adam. Hello, Adam. Nice to see you in the group. So Adam's asking, what is the best way to test or characterize the strength properties of faults and fault damage zones? And what failure criteria are best suited for these materials? And this is directed at the whole panel. So if there's anyone that feels willing to take on this to start, I would welcome you to do so. I guess, Ed, you're quickest to unmute. And or bravest, I'm not sure.
Yeah, reluctantly. I think I was speaking for myself. I think we all struggle with this, or at least we do at SRK is working through that. I think what we're trying to establish is like an auditable approach to characterization, because we know not all faults are created equally. So we don't want to apply one strength to every fault. So we want to understand the patterns and timing aspects first, and then look at the next scale as certain faults and certain orientations, do they carry the same character? Are they all clay, or are they clay with gravel, for example? So at the simplest approach, can you start to bin them into 2 or 3 categories based on their character and how it relates to the kind of timing processes and their spatial location? So I think what we've been trying to do is just establish that auditable approach that someone, a peer can come in and say, okay, I understand how you got there, and I understand how you put them in these 3 categories. If you're lucky enough to have samples of those 3 categories, then you're on the right track. And that could be quite easy if you're in like an over consolidated clay, that you can just pull out that sample from the slope face or get a nice core recovery and test that in a triaxial. If you're in a granular material, then then you've got to look at other means. And is that maybe more the empirical approach? I'll probably stop there before I get myself in trouble, but anyone else?
Well, it's great to hear your perspective, Ed. I see Lauren has his hand raised.
Yeah, just a couple of points. First of all, thanks for asking that question. I think too many times we spend 90% of our efforts trying to get rock mass strength, rock intact strength, and all these other things, when what's really important is the fault strength. And we do the other things because they're easy, and getting the strength and characterizing faults is hard. But it's in many cases more important than all those other things. So it's not easy. And you know, an approach, as Ed is suggesting, where it's audible is good, and classifying into three groups is also good. That's kind of what we try and do, and just try and figure out what's good, bad, and in the middle, and that's sometimes all you can do. The easier question probably is what failure criteria to use. Most often it's some sort of more Coulomb yield. And that seems to work pretty well for a large number of faults. But getting the values for friction and cohesion that faults have does depend on what they're made up of. Is it clay or is it granular? And there's probably n number of ways to tackle that. And the other problem is that faults are change rapidly from one position to the next. So it's again a tough thing to do, but shouldn't be forgotten.
Thanks, Lauren. Scott, something to add? You got to unmute first.
Sorry, I clicked the lower hand button instead.
There you go.
Yeah, I think Lauren and Ed's comments were really good. I thought I'd just touch on something they kind of mentioned, but just how difficult it is to get good samples of the fault materials. The reason being that if we experience loss of the drill core when drilling, the most likely place for it to happen is when we have the weakest core, which often will correlate with these fault zones. And then on top of that, if a fault zone is a mixture of coarse and fine grained material, like Ed said, it could be just a clay zone, or it could be some shear zone, which I would say probably is more common, where it's a mixture of coarse and fine materials. Usually when we have a mixture like that, the best test that we have to characterize that material would be a large-scale direct shear test. And to do a large-scale direct shear test in a 12-inch box, we usually need about 2 5-gallon buckets of material filled to the top. So even if your fault zone is 10 or 20 feet long, you're not going to get that from a single borehole with standard size core drilling. So just getting the size of the sample that you need to do the proper strength test is really difficult in these zones. Some of the best success that I've had is when we have a large fault zone, and once it's exposed in the pit and we're mining the pushback, you can actually go out on the bench and just simply collect from the bench face the fault that you're interested in testing, fill up multiple buckets, get plenty of material, take it back to the lab, and then do those large scale tests to try to assess what the friction angle would be. The biggest thing there will be making sure that when you perform the test in the laboratory, that you perform it at an appropriate moisture content. And the reason being that if you have a lot of fine grained material in the fault zone, its friction angle will change depending on what the saturation level or the moisture content of that material is. So again, it's important to characterize it in the field. Do we think there's any water sitting perched on this fault, which is really common, even if you're above the water table, for water to get perched on top of the fault. And then in the laboratory, you'll want to do your characterization first. So you'll want to do your Atterberg and your sieve before you do the shear test. That way you know about what the plastic limit of your material is, and then you can base the moisture content for the test based on that. Because generally, if a fault zone has access to moisture in the field, its moisture content in situ is probably going to be somewhere around the plastic limit of the material. And so you'll want to make sure that you test it at that in the laboratory and don't test it on the dry side.
Great. Thanks, Scott. Andrew?
Yeah, I think to build on what everybody has mentioned, I think one of the aspects that I focused on in the module that I gave was as well identifying which of these structures could be material to your design process or to the slope performance itself. And so kind of once you focus yourself on one or two of those structures, going back, reviewing what the core exposure looks like, what the actual pit exposure might look like if it's available to you. And then doing a sensitivity analysis on, is the assumed properties that you're going to use for that structure material to the outcome of your design work, your analysis. Sometimes that's not the case, but certainly if it is, that will help you focus your energy on going out and properly characterizing that fault material if possible, or doing further back analyses if you have slope performance data to kind of help narrow that down. And I know that back analysis approach is fraught with its own challenges, but again, I think in lots of times with these faults, if they're material to your design, you're just trying to bracket outcomes and understand and communicate sensitivity of those outcomes to what you're assuming.
Just want to add something real quick to what Andrew was saying is a lot of times when we're trying to characterize a slope, like a stability controlling fault, like we see it in our model, we see it in the core, and it can control the whole stability of a wall. It's really important to go back and truth check that if you get access, if it as you're mining, you expose in the wall and go back and check, because a lot of times those things will change once you have more information. Just like Scott said, once you can collect it from the bench, you might have a completely different picture on the characterization of that. It's a definitely important one.
All right. Thank you, Sarah. Any other comments for Adam? Good question, Adam. Good discussion, panel. All right, thank you. I'm going to pull up a question also from our live group that has a lot of thumbs up. I think it's a good question. So this question is asking if you have a general degree in geology or just coming from, having some base knowledge of geology, this person would like to ask the experts if slope stability and the geotechnical model can be learned through self-study, and is there any roadmap? So at this point, I would be remiss if I did not give a recommendation for the Geotechnical Center of Excellence Professional Development Program, and specifically the course that a lot of the people on our panel today are presenters from. And so I will ask my team here to put that link into the chat to the flyer to find out a little bit more about the course that we were talking about, which is Fundamentals of Open Pit Slope Design. But all of our courses at the GCE are developed with the understanding that you have kind of a base knowledge of, geologic conditions or structures, or just a base knowledge of geology, I guess, would be a perfect start to learn in the course that we are talking about today, which is the Fundamentals of Open Pit Slope Design, or really any of the other courses. So I would recommend that, but then I will ask the panel also if they have any other just tips or recommendations for someone who wants to know more about slope stability and geotechnical model and maybe work at your organization someday. Who knows? How do you train people? How do you take someone from geology to a specialist in geotechnical stability?
Well, I guess I can
Sure, go ahead, John.
share.
Thank you.
I suppose I can share my journey since I started out as a geologist. Getting into geotechnical engineering is it's a pretty easy transition, because most of the time slope stability is often governed by underlying geology, as we said in the initial question regarding geotechnical domains. It often starts with just the underlying geology, structure model, understanding how those complexities are interrelated. And then the engineering side is just applying math and numbers. You know, as a geologist, we like to use crayons, but engineers like to use black and white. And so you just need to, it's a learning process and it to figure out how to apply numbers to the geologic complexity and ultimately it's a matter of mentorship and surrounding yourself with the best people, or people that have more experience than you and are patient enough to take you along that journey. And so it's definitely an easy, well, not an easy, but a long path that I think geology is a particularly useful background to have when approaching slope stability. So highly encourage everyone to explore that route. But I know there are other people, Julia, who have had similar journeys and look forward to hearing your comments.
And
Yeah,
I
I
see you're
think-
getting some good reactions, John. You got the celebrate reaction. Go ahead, Julia.
That wasn't from me, but I will also celebrate John's comments and words. John and I had a similar background. We both went from having degrees in geology into engineering. I later got a master's in engineering, and I would say what that did for me is it kind of gave me confidence that I was lacking before. But I learned most of what I know about engineering from very smart people that I worked with, Scott Selwick being one of them, Dave Nicholas. And so I think John's point about if you've got people that you can learn from, that can mentor you, that can help you understand how to connect engineering concepts with your existing geology knowledge, it is possible. You can also fill that gap through courses like this. Small GCE plug there. But at the same time, I definitely learned a lot from my master's in engineering. But again, I would say the primary thing that it gave me is the confidence in feeling like I really was an engineer. So it's definitely possible. And I think the key is having the right people to teach you and mentor you and bring you along on that journey, as John said.
And thanks, Julia. Lauren, I saw you were next with
Yeah,
your hand up.
just a real quick story and a follow-up. Some of you might remember in 2018 at Slope Stability Conference in Spain, John Reed had a keynote talk, and he's an engineering geologist. And he started the talk out by asking how many people in the audience were geologists. And I think he was expecting that there would be very few. And in fact, I think it was well over half the audience. People at this slope stability conference were geologists. It's a great way to enter the field. I don't think there is one roadmap to a career in what we do. But there is a common element, and that's being curious and asking questions from people, because that's how you learn, and finding the right people who are willing to spend time to answer your questions and direct them, and then ask for opportunities or say, hey, I'd like to try this. I might need a little help, but don't be afraid to get your hands dirty and try some things, and that's also a good way to learn.
Love that, Lauren. And many other people are also loving that. There's lots of hearts going across the screen right now. Sarah?
I just want to do a quick plug because the two geologists that mentored me and, really solidified my base and my understanding of block modeling and are on the call, Julia and John. So it was I almost felt like I had a deficit because I did not have a geology background. So it's one of those things that I picked up on the job, and I learned from the people who, like everybody says, gave me time and gave me their attention. And also it's a matter of finding those people and really pestering them and saying, being available and making yourself available for them to get annoyed with you, so they start helping you. That's my own personal anecdote.
All right, so be curious, be motivated. Any other thoughts from our other panelists?
I just think what everyone said was really great, very inspirational. Just looking at this question on the screen, it says, can it be learnt through self-study? So I wonder if the answer then is no, that's not a good idea, because everyone's story and anecdotes came back to working with a team, having great mentors, working with, other people to share ideas and share knowledge. So, maybe the answer to this question is self-study is not a good idea. You should reach out to other people and join a team somewhere and, go at it that way rather than try to self-study. I just thought that was interesting.
Yeah, real quick, Scott's so right. Like, I think one of the things also about this whole modeling process and the geotechnical model at large is also having other eyes on it. Having the collaboration and getting all the different stakeholders involved, but having, multiple people participate. Good one, Scott.
I think another thing to add too, if you are the type that you want to do a little research prior to joining a team, there are references that are available if you're a reader. There are the guidelines series of books that are put out by the Large Open Pit Project. I flashed one of those on the screen at the beginning of this. Maybe if anyone has the link available on my team, you can throw it in the chat. But there is a textbook, a series of textbooks. There's one specifically on open pit slope design that you could also reference. And there's a website that has all the books, and there are updates currently occurring to the open pit slope design book as well. So I know that's going to come out as a digital book here in the very near future. Maybe not very near, but near future. And Julia stuck that link in the chat for everyone. Any other thoughts from our panel? I am hesitant to bring up another question since we only have 1 minute left. So I think at this point, I will ask for any final comments from our panel prior to closing out the webinar. All right, well, thank you so much for lending us your time, your expertise, your thoughts today. And thank you to all of you who joined us for this webinar. We, as I mentioned, are doing this in alignment with one of our courses that's currently running, which is the Fundamentals of Open Pit Slope Design course, which some of our panel here are presenters in that course for different modules. If you're interested, it is still open for registration, and you can either email us or scan that code there. And I just want to, one more time, thank our panelists again. Without you, we could not do this. So we really appreciate your time today and for volunteering to be here with us. And thank you to everyone else too. We'll see you at our next webinar, which will be on slope design analysis methods. And that date has not been determined yet, but it will be soon. And we'll send out an email on that, or you can check our LinkedIn where it will also be announced. So we hope to see you at the next one. Thank you so much.
Thank you.
Thanks, everybody.
Thanks, guys.
Great discussion.
Thanks, everybody.
Appreciate the
Thanks.
time.
Thank you.
Cheers.